In our video on projectile motion, we derived the trajectory equation, and Lucky claimed that you could use it to build a cat cannon. Now, if you actually build that cat cannon, you probably noticed that something is not quite right with the calculated trajectory. Every time you send the cat on its way, it reliably lands well short of the calculated point. Unless, of course, you build the cannon on the moon. But we probably would have heard about that. So the formula is incomplete because it does not take air resistance into account. But what is the correct way to do it? Welcome to Physics with Lucky. Today we are going to look at projectile motion with quadratic air resistance and derive the equation of motion for this model. However, something rather surprising is going to happen. We are going to reach the limits of simple closed-form solutions. As always, we begin with a few definitions and the initial conditions of the problem. First, we denote the position vector of the projectile by r. It depends on the time t and has two components, the x-coordinate and the y-coordinate. We can write this in the usual column vector form or as a component equation using the unit vectors ex and ey, as shown here. Here ex corresponds to the vector 1, 0 and ey to the vector 0, 1. The velocity is the time derivative of the position vector function, so r dot. And the acceleration is the time derivative of the velocity, so v dot, or equivalently the second derivative of the position vector function. Once again, we use a coordinate system in which y represents the height and x the distance from the launch point. Our projectile with mass m is launched from a height h. The initial position r at time t equals 0 is therefore x0, y0, where x0 equals 0 and y0 is equal to the height h. The projectile is launched with an initial velocity v0 at an angle alpha. We call the x component of v0 v0x and the y component v0y. Because this forms a right-angled triangle, we can write the components in terms of the magnitude of the vector v0 and the angle alpha. v0x equals v0 cosine alpha and v0y equals v0 sine alpha. Conversely, we obtain the magnitude of v0 from Pythagoras' theorem. We have defined the initial conditions. Let us now turn to the force diagram. If we draw our projectile at any point along its trajectory, its instantaneous velocity vector is always tangent to the trajectory. In our model, two forces act on the mass at every moment. The first is the gravitational force Fg, which points downwards. We already included this in the derivation without air resistance. The drag force was still missing from the previous video. This time, however, we are going to include it as well. Air resistance always acts exactly opposite to the current velocity, so its direction changes continuously along the trajectory. And that is going to cause us a problem. We can now express the gravitational force Fg using the unit vector Ey. Its x component is 0 and its y component is minus m times g, where g is the gravitational acceleration at the current location, which we assume to be constant. We already know the drag force from free fall with air resistance. It is proportional to the square of the speed and to a factor k. K is the product of 1/2, the air density ρ, the drag coefficient CD, and the projectile's frontal area A. In this model, we treat ρ, CD, and A as constant. The force must act opposite to the direction of motion, so in the direction minus v. We divide the vector by its magnitude, so that the direction vector always has a length of 1. Vector minus v divided by v is therefore a unit vector that always points opposite to the projectile's direction of motion. Multiplying all of this together gives us the vector form of the drag force. One v can still be cancelled, and now we have both forces. We can now derive the equation of motion for the problem. According to Newton's second law, mass times acceleration equals the sum of all forces acting on the object. The forces are Fg and Fd, and we have just derived them. We divide the equation by m, and this gives us our equation of motion. As we said at the beginning, the velocity is the first derivative of the position vector function, and the acceleration is its second derivative. So the equation can be written as a differential equation for r. And now we simply have to solve it. Unfortunately, it is not quite that simple. But first, let us split the equation into its components. The magnitude of r dot was the magnitude of the velocity, and we determined that at the beginning using Pythagoras' theorem. From this vector equation we can now extract a separate equation for each coordinate. In the case without air resistance, we did exactly the same thing and obtained two independent equations for the x and y coordinates, which we could solve separately. But if we look more closely at the two equations, we find that the equation for the x coordinate also contains a y dot, and the equation for the y coordinate contains an x dot. This coupling arises because the drag force depends on the total speed, which contains both velocity components. Unlike ideal projectile motion, quadratic air resistance therefore leads to a coupled nonlinear system of differential equations. It can be rearranged analytically, but in the general case it unfortunately does not give us a simple closed-form trajectory equation y of x. There is an analytical parametrization in terms of the instantaneous velocity angle. However, the remaining integrals cannot generally be evaluated in terms of elementary functions. So what do we do now? Is this already the end of physics? For such a simple problem? Not quite. But our hope of finding a simple closed-form trajectory equation already ends here, with projectile motion subject to quadratic air resistance. Fascinating, is it not? We do not need quantum physics or relativity for this, not even the three-body problem. Of course, Lucky does not want to leave you there. What a depressing video that would be. After all, we want to enable you to calculate the trajectory of your little cat cannon more realistically within this model as well. So, how do we proceed? For specific trajectories, we solve the initial value problem numerically. We are now going to show you exactly how this works and give you an algorithm that allows you to calculate the trajectories with controllable numerical accuracy within this model. For this, we introduce a time-dependent state vector. It has 4 dimensions and consists of the coordinates x and y together with the velocities vx and vy. In principle, this is something like a phase space vector. We will introduce phase space and explain it in more detail at the next opportunity. Lucky is already looking forward to it. But even if you're not familiar with phase space, that is not a problem. Admittedly, we now have 4 dimensions and I can already see a few brains tying themselves in knots, but ultimately these are just 4 numbers that we have collected in a vector. You do not have to be able to picture it. We could also use 2 two-dimensional vectors instead, if that helps. What matters is that we can write down a time derivative of this vector z. X dot, y dot, vx dot, vy dot. And x dot is vx, y dot is vy, while the derivatives of the velocities are the accelerations. And those are precisely the 2 component forms of the equation of motion that we have just derived. It is also important that z dot, in other words dz by dt, is a function of z. We will use that in a moment. For the next step, we need the definition of the derivative. Who remembers it? Yeah, Lucky does, sure. The derivative of a function z at a point tn is the limit of the difference quotient as delta t approaches 0. However, because we do not know the exact function z of t, we use an approximation over a small but finite time step delta t. We can say that the derivative is approximately equal to the difference quotient without the limit. The smaller delta t is, the better the approximation becomes. And of course, as delta t approaches 0, it becomes exact. For everyday problems, however, it is enough to get sufficiently close. It is probably sufficient to determine the trajectory to the nearest centimeter or perhaps the nearest millimeter. Calculating a trajectory equation to micrometer or nanometer precision would not make much sense. any inaccuracy in the launch angle or even the smallest fluctuation in air pressure would produce a larger error than our calculation. Let us now denote z at Tn by Zn and z at Tn plus delta t by Zn plus 1. We substitute these terms and rearrange for Zn plus 1. And z dot was a function of z. Let us now take a closer look at this equation. What have we got? We have an equation that calculates state n plus 1 from state n after a time delta t. This means that if we have an initial state for n equals 0, we can calculate all subsequent states step by step. This is called the Euler algorithm. We use state n to obtain state n plus 1. We defined the initial state z0 at the beginning of the video. It consists of the initial coordinates and the components of the initial velocity vector. Let us write out the formula for Zn plus 1. And this is the result. From each state we can calculate the following state. And if we want to increase the accuracy, we simply have to reduce delta t. Lucky would like to visualize this once more. We have our algorithm and we begin with n equals 0 and a delta t of 0.12 seconds. The projectile starts at the initial position r0 at a height h, with the initial velocity v0. Using our algorithm, we calculate the position r1 and the velocity at position r1. We insert r1 and v1 into the algorithm and obtain r2 and v2. Then we insert r2 and v2 and obtain r3, and continue in this way until the projectile reaches the ground. Because the projectile will usually cross the ground between two time steps, we interpolate between the last point above the ground and the first point below it to estimate the impact point. To increase the accuracy, we repeat the same process with a delta t that is half as large, 0.06 seconds. As you can see, the trajectory is slightly shorter, so we halve it again to 0.03 seconds. Now there's hardly any change. We can reduce delta t further until another halving produces no visible change. This is a practical indication that the remaining discretization error is small. There are also higher order algorithms that achieve the same accuracy with larger values of delta t. The Euler algorithm is not ideal in that respect. But for our problem, it works reliably when delta t is sufficiently small. And you can now guide your cats to the target as accurately as the model allows. Have fun! And this is Lucky. Right on target, at least according to our model. And he will not be moving very far from it for a while. Unless there's food, I guess.